Hey y'all, it's Friday today and I'm making these videos for you for next Friday, which is going to be 6.3's lesson. So I'm going to do page 340 numbers 13C and D and just go through some methods for sketching the graph of a transformed logarithmic function. So let's start with part C. The function that we're given is f of x equals 5 log of 2x minus 4 minus 6. So in the activity before watching these videos in this lesson, you should have used the Desmos graphs to get a table of values for y equals log x, our basic log function, and we can use 3 anchor points from that one because the points are kind of far apart, so we can't go to the negative side because we saw that log is undefined at x equals 0 and negative values, and then it jumps up by a power of 10, so we don't really want to go up to 1,000. That's not very practical for putting on a graph. So 1, 0, 10, 1, 100, 2, those will be our anchor points for y equals log x. And when you looked at the graph, you should have also noted that there is a vertical asymptote at x equals 0. And so just to recap, the graph looks something like this, where the x-intercept is 1, and we have a point at 102 out here somewhere, and a point somewhere around 10, 1. So this is just a sketch, obviously. Okay, and so that's what our basic y equals log x looks like. Now we want to transform this into the graph that we've been given, and so I'm going to do it with a mapping notation. And so my mapping notation from the equation that I've been given, the transformations that affect x. Oh, before I go ahead and do that, there's something that is very important that we need to remember to do before we look at what our transformations actually are. Oh, you know what? I've forgotten how to get my different colors. Ah, here we go. Okay. We need to be careful about this 2 here, right? It's got to be factored out of the entire bracket before we look at what our transformations are that affect x. So let me just rewrite this function over here, factoring out that 2 first. So 2 bracket x minus 2 minus 6. And all of this part, the 2 bracket x minus 2, is inside the logarithm. Alright, now we're ready to actually do our mapping notation. So x, y, no, let me fix that. I don't like the way it looks. Any general point x, y will be transformed by the transformations that affect only the x coordinate, which are the 2 in front of x. Remember, it becomes the reciprocal, so that's 1/2 x. And the x minus 2 becomes a plus 2 because that is always the opposite sign for a horizontal translation. And then our y value is affected by a vertical stretch of 5 and a shift down by 6 units. So that's my mapping notation. Let me just move over to the next page and rewrite that mapping notation. So xy is going to become 1/2 x, I believe it was plus 2, let me just double check, yeah, plus 2, and 5y minus 6. Okay, so let's now take that and apply it to our general points for anchor points for log y equals log x, which are these ones here. And if we do that, then our table of values becomes 2.5, -6, 7, -1, and 52, 4. You might want to just find those points yourself just to make sure you don't have any trouble doing them. Okay, now we should transform our anchor points, but it's also really important to take a look at what happens to our vertical asymptote. So our vertical asymptote, if we go back here, recall that it was x equals 0 for our basic function y equals log x. What happens to it? Well, according to our mapping notation, we have a horizontal shift 2 units to the right, and that is the only thing that will affect our vertical asymptote. The horizontal stretch or compression does not. None of the vertical transformations will affect it because it's always in terms of x. So x equals 2 is our new vertical asymptote. It's been shifted 2 units to the right, just like all of the points on the function. So now we're ready to do a sketch of our transformed function, which we should always start with where our asymptote has shifted to. I'm going to actually move this back a bit because I have to get up to 52. So 2 would be, let's say, somewhere here. This is my new vertical asymptote. And then I have a point at 2.5, -6. 1, 2, 3, 4, 5, 6. So somewhere down here, just to the right of my vertical asymptote. 7, -1. I'm going to put that pretty close to the first point. And then somewhere all the way out here, I'm going to put 52 on my x-axis, and that corresponds with a y value of 4. So I can, now I'm going to try and join these with a smooth curve on here. Not so bad. It's a little harder to do on this tablet than it is on paper. Okay, so my transformed function looks something like that, and you should always just look at it, make sure that it makes sense. My vertical asymptote has been moved over 2 units to the right. Hang on here, let me just get a different color so I can highlight this for you. So my vertical asymptote has been moved over 2 units to the right. My graph is vertically stretched by a factor of 5, so it looks kind of longer this way, stretched out. It is moved 2 units to the right, that's the vertical asymptote, and then 6 units down. The 6 units down you can't really detect so much in the way the graph looks. Okay, so that's it for part C. I think I'll start a new video for part D.